Hello, welcome to my channel. In this video, we are going to be taking a look at the Faraday's law of induction. So we'll start with the Ampere's law, which states that when a current flows through a conductor, magnetic field will be generated. So Faraday, during his time, noticed that when current flows through a conductor, magnetic field will be generated. So he thought that is it also possible for magnetic field to also produce current? So that was how he started with several experiments. And one of the experiments that he carried out was something of this form in this diagram. So this time around, we have the magnetic field, which is going to be acting as a current. Then we now have the loop, which will have an induced current, which is going to act as a magnetic field. So in this process, we have the bar magnet moving to and fro. Then the magnetic field cuts across this loop, this circular loop, right, made up of a conductor. So as long as this this bar magnet moves to and fro inside this loop, there will be an induced current, which will be detected by this galvanometer. So that was how he was able to come up with the idea of using a magnetic field to generate current. And we start with this formula, which connects the magnetic field and the area of the loop, which is giving us the magnetic flux is equal to the magnetic flux density times A, which is the area of the loop, then cos theta, which is the orientation of the loop. Okay, so Faraday, from his formula, said once this particular magnetic field is differentiated with respect to time or changes with respect to time, then there will be an induced EMF. So we have induced EMF equal to minus d phi b dt, where our minus here comes from the Lenz's law. So we have our induced EMF. So we notice that once this one changes with respect to time, there will be induced EMF. Then this expression can also be rewritten as E equal to minus n d phi b dt, where our n here is the number of loop. And that means that once this number of loop, this one is only one loop. So if we wrap this particular loop several times, that is taken care of by our n here, so that as the number of loop increases, it also affects the induced EMF. It increases the induced EMF. Now that we have our file B, which is equal to this, we can replace our file B as BA cos theta. So we have induced EMF equal to minus n d into bracket d BA cos theta. Now for this EMF to be induced, right, one of these three parameters must change, right? One of them must change and the other two will be constant. So the first case is when we have our B changing and our A is constant. When this one is constant, it means that our theta here is 0. So cos 0 is 1. So that's why we have this one. The second possible case is when our A is changing and our B here is constant. There will also be an induced EMF. So for us to have an induced EMF in this particular loop, either B is changing or A is changing, or finally the orientation, which is cos theta, is changing, then BA is a constant, right? So these are the three possible scenarios. So let's look at situations that have these ones in common, or that connects these particular ones. So we have the first possible case is when our orientation is changing, we have this kind of setup. This is a typical example of when our orientation is changing. So we have the magnetic field across these two bar magnets is constant. The loop here, the area of this loop is constant. It doesn't change, but the orientation is changing, which means that this loop is rotating about an axis. So this is the formula for such scenario, right? And the kind of currents or the kind of induced EMF that is produced, right, is an alternating EMF. Then secondly, where we have our changing A, Then this is a diagram that describes such a scenario. This is a slide wire generator, right? We can see this is a loop, this is a rod that moves in this direction. So we can see the area here. At one instance, this is the area. At another instance, when it moves to this point, this is the area. We can see that the area is also changing with respect to time. While our magnetic field, which is represented by these crosses, right, is constant. So in this scenario, we also have induced EMF. Then thirdly, we have our magnetic field that is changing with respect to time, where our A is constant and the orientation is constant. We have this particular one. So we can see that the area of this loop is constant, the orientation is constant, but the amount of magnetic field that goes through this loop changes with respect to time. If this loop moves towards this direction or this one moves towards this direction, we see that the amount of magnetic field that will enter this particular loop will be different from when it is at this point. So at this point, virtually all the magnetic field lines will enter this loop. So that's a change in magnetic field. So that's it. So next thing we are going to be looking at is the differential form of the Maxwell equation. So we start with this formula, which is the induced EMF equal to integral of electric field times dot the length, the displacement, right? Also, we also have, recall that our magnetic flux is equal to magnetic flux density times area times cos theta. This expression can be re-expressed in an integral form as flux, magnetic flux equal to integral of B dot our n cap ds, where this one is the area, right? The change in the surface area. This is the surface integral. Okay, so we also recall that induced EMF is equal to minus d phi dt. So if we differentiate this one with respect to time, we also need to differentiate this one with respect to time. Let's see what comes out of it. So we have d phi b dt equal to dt of this one, right? Now, if you notice, this expression here is exactly this expression. So if we just introduce minus sign here, then everything here will be equal to induced EMF. Everything here will also be equal to induced EMF if we introduce minus sign here, because this one is exactly this. Introduce minus sign, everything here will be equal to induced EMF. And our induced EMF is equal to this expression. So if we introduce minus sign here, everything here will be equal to induced EMF equal to this expression. So we have this expression here. So at this point, we now have that this dt can go inside and it reduces to just this one, which is this, equal to minus our d dt has gone inside to meet this expression. So if we recall from Stokes' theorem that there is a connection between the line integral and the surface integral, we have the line integral, which is this, is equal to the surface integral. So the left-hand part of the previous equation, which is this, is equal to this using the Stokes' theorem. So if we agree that this is equal to this, then we can recall that if this one is equal to this, that means this one must be equal to this. So we have that this expression, which is this, is equal to this expression, which is this, from Stokes' theorem. This is a connection between the line integral and surface integral from Stokes' theorem. Now, therefore, everything here must be equal to this expression. So now that we are interested in this part and this part, we can ignore this one. Then we'll bring out this one and this part. So at this point, we can see the connection between them. There is something that is connected between them, or something similar, which can be taken care of. So we see n ds. So we can take care of this one. We can see integral of s. We can take care of this. So what we are left with is that this inner expression, the curl of E, which is the electric field, must be equal to the differential form or the derivative of B with respect to time. So that gives us this expression. So this is the Faraday's this is another way of representing the Faraday's law of induction. and it is one of the equation in the Maxwell equation, 4 Maxwell equations. I hope this helps. Please like, share, and follow for more, and also subscribe. Thank you.